We're good. Okay, today, I'm taking over.
Oh, you're having problems with these?
Not really, I just had one, I had a question on one of them.
Was it the average one?
Tell me, you'll do. Do you have a problem with these, Matthew? What do you have a problem with?
I never got this answer.
Which one?
Number 52. Yeah. The frequency should have been 1 over P,
No,
right?
we'll go over it. Just tell me which one.
Number
2.
Number 2. What is the frequency of the oscillation of the wave? Okay.
That's 2 pi over.
1 over P, yeah.
The period is 2 pi over the W.
This is for the second question? This is, yeah, for the first question. Okay, what's the problem?
Well, mine should have been, actually, it's inverted.
Omega equals 2 pi f, right? So
17.9 over 2 pi was equal to 28.12, but the answer is 2.8. Or whatever. It's 1/10 of that. So what did I leave out?
How is 17.9 over 2 pi is equal to 28.12?
Yeah, how did your number increase?
Two?
That's about 7. That's 3.14 times 2.
No, maybe I had it in my whatever it was wrong. But the first time I came out with it wrong, so I was like, hey, I'll write it out so I can see what's wrong. Because I couldn't figure, I was like, what the hell? I did the same exact thing you said. Then we got to take it for the velocity and the acceleration. We got to take it with respect to time, right?
Yeah.
Okay. Then, I don't know what else. The next is next page. The next is the second set of problems. So then I got to get on the second set of problems. So I'm good with the first set.
So yeah, it's I mean, I don't like. I mean, it's not that I don't like the concept of waves, but again, they don't really explain it right.
I don't know what you just said.
The entire way they present stuff.
From the pre-auction?
Yeah. I mean, this is supposed to be the introduction to light or RL circuits. It's like an introduction to RL circuits just for the description of the wave, and then in bigger introduction to light, because light is wave. But I mean, why do they even get into the velocity and the velocity or acceleration of the wave, and why do they even get into tension or whatever?
Because the next lab is about tension and the same thing.
Is it?
Man, I'm just trying to make you feel better.
Okay.
Did you have any questions?
Huh?
No, that's a Matthew Kim question. That's what you
What's up?
said. Oh, yeah, I forgot. I don't know how to use a calculator. That's something.
Alright, what's up?
The average velocity question.
Okay.
I don't, like, this should just be an integral, but I've scribbled it out in my folder. But we have a function, and the phase shift isn't really important for this, for an average velocity. The important part should be, like, the first little hump, you should be able to get the average velocity from that.
And then divide it over 2.
Divide by 2?
Well, divide it over period, not 2, over half a period, sorry.
Yeah. Which are.
Which one is that?
It's 7 or so.
Average speed?
Yeah.
Average velocity. It's average velocity.
Average
Speed.
The speed, I'm sorry. If it was velocity.
Yeah, this is the thing about this. It says so average. I mean, it doesn't even specify it. So unless you watch the 3 lectures and know what they mean by average speed, you're not going to be able to answer.
The
what
discipline
it
is the absolute value, so that never goes negative.
But which speed?
What?
Because there's 2 speeds here.
Oh, the up and down speed.
The up and down speed, yeah. So the up and down speed. If you want to find the average speed, which is the up and down speed of a wave, right? So what would be the average speed of something that's going, let's say,
Delta T over delta X. I mean, no, delta X over delta T.
basically, yeah. So delta change in displacement, not displacement, change in distance over change in time, right?
Which is displacement.
So-
What's right?
not exactly. The distance and displacement are very different. But yeah. So what's the distance if this goes up another A, goes down another A, goes up another A, and goes down another A. That's basically what they want. It's just 4A over T time period.
Oh, T is period, I forgot that. Keep switching the notation.
T. T then. Yeah.
Damn it, why didn't the integration work? Because I tried getting the velocity function and then integrated
We're
that.
only talking about the y velocity here. This is wrong. It's only the y velocity. So how many times it goes up and down? This actually is the y velocity. This actually is the y velocity. Because no, this is not the velocity, but yeah, they mean by the y velocity. I'm not going to draw velocity. It's kind of confusing. But so as you're moving, as this is moving like this, it's also moving like that, right? Because so, like your example, like string. They're just talking about the velocity. They mean by the velocity is how many times. So I mean, how fast you're moving your hand up and down, right? Since it goes here, here, and then back here, that's one period, right? Because when you move your hand up, this goes up or something. Then move your hand down, it goes down. Everything else goes up and down and down. So you move your hand up, one amplitude. You move your hand back to the 0, that's one amplitude. You move your hand down, that's another amplitude. You move your hand back.
And that's 4 amplitudes.
That's 4 amplitudes. 1 amplitude, 2 amplitudes, 3 amplitudes, 4 amplitudes. That's one period. So that's the average velocity of your hand movements.
I'm still angry because the integration didn't work.
What do you integrate?
Because I was thinking, like, you take the derivative of the function, you'll have the y velocity at any point, and if you integrate over a course of a period...
You integrate what?
Over the course of a period, like, you integrate half of the period.
Integration from 0 to pi over 2 of...
And that's 0 to 2 pi.
Yeah, it's 0 to 2 pi, but I don't think it works. But pi over 2, 17, 2.15 cosine 2.6x.
I feel you should be able to get it to work by integrating it, but...
That's not the y velocity, though. That wouldn't be the y velocity.
What would that be?
That would be the... So as this... So let's assume this is a path of a particle, right? If this is a path of the particle and it goes, right? And the derivative... if this is the... If this... Why would you work for integration? I mean...
It should be, because...
If this was the velocity... this was the velocity, it would make sense, but it still wouldn't work. So if this was the velocity, if the wave equation was the equation of the velocity, the integral of the velocity over t would give you the average velocity, right?
Yeah, that's how I was
But this is basically you can think of the wave, I guess, as the motion of a small particle.
Or you can just take the derivative of it.
Okay, you take the derivative of that.
And then you integrate that derivative.
Which is the same as what you had, and divide it over t. But then again, that would give you the that would give you the average velocity.
I'm just surprised it didn't mathematically work out.
You have to integrate over the entire time period.
Couldn't you just integrate over the first portion of it?
Over this portion, then multiply by 4.
Yeah.
But then there's a negative component here, so there's a positive
But
component. But
speed, so you're not interested in the negative.
So you multiply by 4. Let's see. Why wouldn't that work? Why do we have a binary search tree here?
It's from there all day. Can't go wrong with them.
Okay.
Maybe I'll need to put the numbers in again.
That wouldn't give you the y velocity. That would give you the velocity of the path. Velocity of the direction of the path.
I got the idea from the pre-lecture video. Because at some point they took the derivative to get the y velocity.
So that should be the derivative. Alright, so it's just a motion then. So what's the way described as sine? What is it?
Y x comma t equals the amplitude sine.
I mean, what it'd be one in the homework, particular one in the homework question that you have.
All the exact numbers.
Yeah.
Oh, okay. Equals 0.15
0.15
sine
sine
of 2.6 x plus 17t.
Okay, so let's let this be at x equals 0. Let's say we're integrating at x equals 0. 0.15, the integral from 0 to
2 power.
let's see, 4 to pi to the whole one. Sorry, it's not integral, actually.
What are you doing, taking the
Because,
derivative?
because no, we're not taking derivative or integral, we should just divide this from, so it should be 0.15 times 4 sine of 17 t, the first one is going to be 2 pi over 2, and don't pay attention to this, continue doing. Do you have mathematic up here?
That people program?
Huh? Evil? Evil?
Sorry, I just don't like the language.
It's amazing, man.
I would have just preferred to see. Well, it is pretty amazing, but at the same time, I feel like it's unintuitive. It's not an expired.
Yeah, this is actually, it hasn't, it's...
I just threw it in the calculator now if you want to see.
Yeah, you can do that. This is 2008, actually, Mathematica 2008. They haven't renewed it since 2008. It's not 2008, sorry, Mathematica 8, which is way.
It's still going to expire on us now, too.
No, they renewed it.
Oh, did that? Okay.
That's why I'm happy.
Oh.
I thought I'd have a few days without Mathematica.
Would that be a bad thing?
Yeah. For me, yeah. It'll take me 3 hours to do whatever work it wasn't for Mathematica.
0.052.
Hmm?
0.052.
0.052.
So it seems small.
Let me see your numbers. Let me see your numbers. So,
Actually, that should get the right answer, come to think about it. I think it should get the right answer. I don't know. But it's not.
yeah, this one right, that one. You didn't check.
This one's right. Number 8 is the only one that's wrong.
What is the right answer?
For what?
For this one.
For 8?
Yeah.
Oh, I've not Bill. I've tried 17 times. You said originally it was 4A over
Yeah.
the period?
Yeah.
I'm trying those numbers here very much.
So, number 10, on the same row, how would increasing the wavelength of the wave change the period of oscillation?
It should be, right?
So mine, well, if you look at, because it didn't say the velocity changed. So the velocity
Hold on.
of the wave times the period is equal to lambda. So if you increase this, the wave stays the same, this has to increase to stay with this increase. Yes?
But the,
Using the wavelength of the wave change the period of oscillation, right?
Correct? So if that increase, that has to increase. Because they're directly proportional.
Let's see that thing.
I didn't read the second part. I don't do the plan, I didn't really look at it. But I did the what's called the pre-lecture.
Did you get anything?
even distracted. Right, so increasing the wavelength does increase the period of oscillation?
Using the wavelength should increase the period of oscillation.
Okay, I don't know how I rationalize the other ones.
Why wouldn't it?
I don't know, I think I was playing around with the formulas and they canceled out somehow. Algebra errors and...
Yeah, I mean, if you increase the wavelength, it's going to take it longer to get to that same period. It's going to take it longer to go back to right. It's just an efficient wavelength.
That's what intuition said, but I don't trust it.
Doesn't give the right answer.
Okay. For the four times the amplitude of the period. 1.623 for that, and then 0.05 blah 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 for the first one.
Oh,
I got it.
hold on. We did it wrong, sorry. It should give the right answer.
I just
Yeah.
got one.
No,
No.
so what's the period? What's the period in your question? This is wrong. This is wrong. So, okay, what's the period in your question?
0.3696. It's 17 times 0.15 times sine of the period minus sine of 0.
Over. No, sine of the period over 4, because we're doing it. Because you said you wanted to do from here to here, right? and then multiply by 4.
I did it to half the period, so in the middle.
Half the period, isn't that going to give you 0? Wait, no. But I mean, if you're doing what we're doing, yes, it's going to give you 0, but because, I mean, what we're doing is just, because this is described as a distance, and the average speed is the distance traveled over time, right?
Yes.
Right? So if you say,
I just integrated the whole first hump.
you integrate, but you're integrating distance, what does that get? Sorry, you're integrating it. So that only, so that gives you the average distance, if you divide that by t. So if you want to integrate, you can find the, I guess you can find the derivative of that and divide by t, which is going to give you the same thing as this finding this minus that. So if you want, you can find the derivative of that and integrate it from 0 to something.
Mm-hmm.
I guess you can do that too. So
Oh, it had to be over the whole period.
over the whole period. Over the whole period, it's the average is going to be
Like, but now this formula works, now that I did it over the whole period, because I was doing it, I was integrating from 0 to half the period before.
If you divide over half the period, that's fine.
Wouldn't you be multiplying by 2?
Oh, half the period. Sorry. Yeah, right. Multiply by 2. Like a quarter of the period. Yeah, multiply by 2. But I mean, the problem is.
I thought this would add up to 0.
What?
I thought it would add up to 0.
Half the period.
If you integrate the whole period.
If you integrate the whole period, yes. That's why.
It didn't.
That's why this is no. This is it wouldn't add up to 0 because it depends on how you do it. So if you're integrating from here to here, that's going to tell you the displacement, and the displacement is 0 because you're going up and then down and then back up, which is the same thing. Y displacement is 0. Right? So if you integrate, even if you go half a period, the displacement is also going to be 0.
Oh, that be 0.
Oh, it was 0. Because your distance, because your y, the amplitude, you're going up and down the same distance, so it's up. Up is positive, down is negative. They would cancel.
So you can do, if you want to do this integration, you can integrate from here to here, and then multiply that by 4, divide it over. I mean, from here to here, which is period over 4, because if this is 0.36 whatever, this is 0.36 whatever over 4. So you integrate from here to here. Then you don't even have to integrate. I mean, it's like you're gonna find the derivative, then integrate. Just do the original function.
Mm-hmm.
I mean, the original function at. So this at.
Well, you can't just do the original function
You can't.
because there's going to be a constant from taking the derivative.
No, you don't get a constant for taking the integration, and we're doing a definite integral. Since we don't have a constant. Right? You integrate, you don't have.
Oh, like, here's like you have the original function,
Right.
and the time period is 0, and then you take the derivative, and you get that. Oh, this logic, never mind.
Wait, why is it? This should make cosine 2. Wait, where's the t component?
I was thinking at t equals 0.
At t equals 0, but you're integrating with respect to t, so t is a function.
We
So
could
this is a constant. If you're integrating this with respect to t, this is a constant. This entire thing is a constant.
Can't you integrate with respect to x?
That doesn't really tell us anything about that velocity. So the wave. So what's happening with the wave is that this is changing with respect to t, and this entire thing is changing with respect to x. So it's just like a sine wave. It's just so. You have a sine wave that's moving, right? Its motion here, it's a function of that. Its displacement like that is a function of t.
Yeah.
Right? That's why, so, this is moving like this as a function of t. It's going up, down, up, down, up, down. And this entire thing is also moving like that as a function of x. That's why if you take x equals 0, you get this wave. Sorry, you get, no. If you get, if you take, in this question, if you take x equals 0, you get that wave. No.
Is that a cosine wave?
Yeah, sine wave. If I had cosine, yeah, sine wave. We get a sine wave.
Mm-hmm.
Albridge already knows that I know my sine and cosine. Continue. Yeah, if you take x equals 0, you get this. A sine wave. If after, I mean, at a different x, the wave is going to be like this. The entire thing, all the shape and the general thing of the wave is going to be the same, but it's going to be moving like that. So the entire, it's not only moving like this, it's moving like this.
I thought the t component was the shifting.
The t component is the up and down thing.
Oh God, I've got it completely mixed up. I've been thinking the t was the shift and that the x component was just the up and down part.
K, this is K. Now the t is the up and down part because it's negative.
Because why?
Because it's the because of omega. Omega.
Why can't that part come first? Oh, that's nice to know. Now I'll make it much less confusing.
Huh.
Can we do some numbers real quick?
Hmm?
Second set. Yeah.
I'm going to confirm that first, so I'm going to jump second.
Did you start on the second set, Matthew?
Oh, I started a little bit and actually didn't.
You start on like number 12. I mean, you do number 12?
Number 12.
No.
No.
I mean, the second,
Oh.
the second set.
No.
What is the speed of the
Speed of the
wave
wave
pulse?
pulse.
So it is linked on T. See if that's correct. I don't have my own, let's make sure. So the wave is 723 divided by. Can you see if 16.98 is the right answer?
Sure. Did you go through most of yours?
You're right, Matthew, actually. I'm sorry, you're right.
I don't know if I understanding.
Yeah, just forget everything I said. You're right. Yeah, it's because, I mean, yeah, multiple reasons for it. Because when it's negative omega t, it's going the other direction, and that doesn't affect the x. So the wave is just traveling in the negative direction. Yeah, it's negative. Yeah, omega t is a function. So yeah, if you freeze t, you're gonna get that wave. Sorry, you're right. You're right.
Easier again.
So yeah, you should be integrating x actually, not t. You should be integrating x.
Because then if it's x, you already know what the period is. Yeah. The period is a distance, right?
Yeah, the period is crazy.
Of the wave, like of that whole sine wave.
Period is the time that it takes it to travel.
Yeah, trial to trial or top to top, just whenever it repeats itself.
Right.
If you think of it as like a normal sine wave, the sine wave repeats itself every 0 to 2 pi, and 2 pi to 4.
Yeah. So,
Which one are you stuck on? This one.
Wavelength of the wave pulse.
yeah.
Oh. Yeah. What should I use this one right here? What do you contemplate?
Huh?
What do you contemplate? What's the average speed of a piece of the slinky as a complete wave pulse? Is that?
I was thinking it's the average speed or something. Or A over T. That would
What is the wave?
be. What's the average speed? What's the average?
0.29.
What's the period?
143.
1 over 4.8.
Should be.
So it should be VT.
Speed for A over T.
How did you?
You said 0.8 over T, right?
Yeah. Travel the distance of 4 A in 1 T. Oh, this is why I don't like weights. This is why I don't like weights. There's so much going on. Alright, so I'm trying to figure out if the period of the wave is related to the T or the X.
That's a
Is
good
what?
question.
What is what?
It's related actually, it should be related to both of them because look, I mean, if you have a stationary wave, this is the time from here to here, it's going to be the period, which
Right.
is the same if you have the same T and this wave is moving from here to here, the time this part takes its track, this part, that's going to be a period.
Which is the same thing you just said twice.
Yeah, but I mean for a wave, because, I mean, is it related to this component or this component? That's why it's related to both.
You didn't even put an answer. Oh, okay. Well, now, so 3, didn't you put that in there?
Let him do it, Eldridge.
No, I'm just using his numbers for, you know. See, I gotta use his is right, then my process is right. And he just happens to get the answer, but he know this solution we talked to him.
What'd you do?
I'm trying to figure out what is the average speed of a piece of the slink as a complete wave pulse
Okay.
passes.
And what did you do?
4A over T.
4A over T, okay. And that's wrong.
That's incorrect, that's correct.
You're in 0.29 and,
Well, no, I use his for him.
oh, you used, which
So here's this
which
point
T
two
did
for
you use?
A.
Which T did you use?
0.43.
This T?
No, I use his.
I know, but I mean,
I know, but I physically use his because we
I know, yeah,
use his.
yeah, it takes, that's the time it takes to travel through the entire thing. Not the time.
Oh, is that
So not the
period?
period. That's not the period, no. This is just one wave pulse. So that's
Oh,
one wave
so
pulse,
what's
that's
the
moving
period?
like that. That's how they think about it. And they just think of the sine function that's
Okay, so it should be times 2 then.
No, that's
That's entirely.
That's the sine wave moving the entire thing. We're talking about the period of the sine wave. If they give you the frequency of the sine wave, you can figure out the period of that.
Then what does that T represent?
That's the time it takes it to
Probably the whole length.
the whole length of the slinky. So this is your star here. And you have a wave that's traveling throughout this, so a sine wave that's traveling like this. So it starts like this, it's a pulse, wave pulse. So just this comes here, and then here, and then here, and then here. This one wave pulse, not an entire wave, just one wave pulse that's traveling from here. They say it takes a time t equals whatever to go through from here to
The
here.
entire length.
Right, yeah, the entire length.
Okay, so the frequency of the wave pulse. So we need to use 1 over F then, right?
Yep.
Okay. So I should
Find the
have used.
period of a wave pulse. Don't use his numbers, don't submit anything for him, just ask me and I'll tell you if it's right or wrong. I can get that, I can see your answers.
You see my answers here?
Yeah. I'm not gonna show it to you, but I can see your answers.
I haven't asked before. Okay, like number 15 for me.
Tell me, I'll tell you.
I was looking for lambda, so I should have V and over frequency, right? Would that be right?
15, what's 15?
What is the wavelength of wave pulse?
Lambda of the wave pulse. Did you change anything? No.
So that should be right, right?
Yeah, should be right.
And it's not. So my velocity I got, my speed I got is 16.029. I don't know if I answered it right, but I think they are. I mean, I would end this one called 0.43. Oh, no, I don't. I put the wrong number in there. 16.029. Times 34.85. No, I don't know. 16.029 divided by 0.46. Yeah, 34.85.
Yeah, 34.85.
So the average speed should have been.
The speed, not the. Okay, next one.
Yeah,
Speed, it's a thing here. What's up? What's up? What are we doing now? We finished that? We finished what we were debating on? Something new come up? What's up?
Yeah, moving away false one. Could we model this?
Did you finish
What's
the
my
question?
Yeah, that's all done.
Still good. So the average speed should be 4A over the frequency, right?
No, in times frequency. Over t. Over time. Over the time period. Over
So
its
times
period.
F, so it should be F, 4AF.
Okay.
You want to model it. The problem here is that it's just one side wave. One side wave.
They give you everything you need, don't they?
Yeah, basically. Yeah, oh, for modeling it? Yeah, but I mean, so you have one side wave. I'm just thinking how, because it's not an entire wave, so you can't give an entire wave equation.
Why is it?
They say it's a wave pulse. A wave pulse. It's a wave pulse. One pulse. It's not the entire wave.
Just going through it.
Yeah, it's one wave pulse going through it. If it was a wave, it would be the entire thing going through it. This time it's just one wave pulse going through it. It's one side function. Like one period of side function going through it. That's a wave pulse. So yeah, if you want to model it, I guess you can do it with a period, a specific period. Like define a sine for only one period, and then give it everything it needs.
The time for one period. Oh, okay, yeah.
Instead of sine for everything, and restrict it on that period, and restrict and let x go through the entire length of this. Like no, sorry, t go through the entire length of the thingy, and x goes through one period. Yeah, T would go.
Okay. So if I'm doing the new tension in a second. Check it. So T, V squared, the new mu, right?
What is it? What'd you get?
17.064. Some 16 for me.
No.
I think so.
What's it?
Tension, I'm using, my tension is equal to V squared mu.
Right.
And with the new length. And then it says what's the new mass density, so then I'm supposed to do
What's v squared?
16.029 squared. Or was I supposed to use this?
No.
Okay, so it's.
Yeah, 16.0. No. Okay, and the new squared and 0.
And the length is stuff. So stretch the process to make.
Right. Oh, 12.
don't think I can use that because I have this, so I gotta do something different. Mass, what was the new mass density? Oh, the mass density, okay, I got that. So that would be the mass density here.
Huh.
Calculation, let's see. 14, 17, 14.
Okay, the tension should be twice as much. Shouldn't it? Okay, just stretch something twice as much, the tension should be twice as much. I didn't think of the spring. Spread tension is twice as much.
So, okay. Yeah, because when you use this,
X, yeah, doubles X, doubles X, doubles tension. But it's
so K is
not working.
the constant is the same.
It's not working. That means there's a. Oh, okay. Okay. Doesn't B squared A be change?
Where? Why?
Because you don't. You're cutting the period in half.
That ain't nothing to do with the velocity, with the speed of it, though. It's still traveling, it's probably at the same speed, you just got to go longer distance.
Longer distance. You shouldn't change any, right? This is weird. I don't like waves. I don't like waves at all. Yeah, 17 is right.
Instead of 14 right now, yes. What is the?
what does the W represent? Is that how fast it's moving? Yeah, omega, sorry. Like how fast that portion of the wave is traveling through the space. Maybe. Or is that how?
Yeah. Because it's 2 pi over period, right? Period is the time it takes it to go from the beginning to the end of the wave. And 2 pi is that distance, right?
Yes.
2 pi is the distance in axis.
Mm-hmm.
So it's 2 pi, so it's the distance over time, which is the speed of the
So while you're racking your brain over there,
What?
while you're racking your brain,
Oh, God, man.
I need, so number 18, I know how to find lambda. I need to find the frequency. But Newton.
Hold on, can you just...
No, you have to be bombarded with all
Hold on,
these things,
brother.
and until you should be able to multitask. Yeah, there you go.
What's the problem? I'm not gonna tell you it's right or wrong the last thing because I just realized they're time questions. But here's the deal. They're assuming that the length doubles. I'm trying to figure that out. They're assuming that the length doubles when you stretch it. The length of the wave doubles when you stretch the slinky. Now I can see that happening because it looks slow. I can see that happening. Why does it double? Because it does not.
So the time should double.
The time is the same.
But if the velocity hasn't changed,
If the velocity,
and if the length is the same,
sorry, they're assuming that the velocity doubles. Yeah, they're assuming. They're assuming.
you can't assume that.
They're assuming. I don't know how they're assuming that the length of the wave doubles, because which means that the velocity doubles.
No, it states slinky stretch is linked, but the total mass doesn't change. So mu does change.
Now the slinky is stretched twice the length. The mass isn't changed. What is the new tension? So the slinky's is stretched down to double the length. For some reason,
They're assuming the speed of the wave is traveling through the doubles.
Let's say it gets there at the same time, though.
it gets it there at the same time. Yeah.
But it doesn't tell us that, so how are we supposed to assume that? You see what I'm saying?
I know. I understand.
So you're saying the velocity doubles.
Also doubles it, so I get that at the same time. So that would give us the right answer here. Because it's twice, but I'm trying to explain that.
So that's what it should be. I just can't buy that. I mean, when people said it's in the same period, I mean, pick that one off.
I guess they're assuming that the time it takes it to go from here to here is that much. It's n takes t point is 2, 0.
Okay, so the frequency stays the same.
The frequency, yeah. So no, I guess I'm not sure about their question. I mean, are they asking if they're asking that? Now let's assume that it's stretched twice as much, as in go back to the first and change this to twice as much, and you leave everything the same. Is that what they're trying to say? Because if that's what they're trying to say, it makes sense because they're telling you 0.418.
So they're saying assuming the slinky axis that obeys Hooke's law, which is here, so this increases, which is the tension. If this increases, so K is a constant.
K is constant, yeah.
So we're saying this is 2x.
Yeah, 2x.
Okay, so if we follow that, and I get it. No.
What?
Because if that was true, then the tension would
double.
You know what?
Dividing over two.
Because it's found intention right there, so that will be correct. And we follow Cook's law. Okay,
Yeah, if you follow this law, that's double.
yeah, because we double from here to that. So what is the new time increase in the world once you travel down the slinky? So that'd be 2T.
Right.
Because it's double, so to one, we're supposed to travel that. One period was this time, so if you doubled it, it has to take twice as long to get there.
But I told you there's something with the, I guess,
So the velocity doubles, it should go in the same amount of time.
but yeah.
Well, hold on. Velocity doubles. So then it would be L over V then, right? So if the velocity doubles and the length is double, we're in the same spot we were in at first.
Yeah, the time was
Am I incorrect?
no, the time is the same. And the length of the wave doubles,
And
which will be the time.
velocity double.
Yeah, I mean, the length, the velocity is gonna double because of time. That's
Those have to be the same, they have to be simultaneously. She's twice the length and twice the width is the only way that T is going to stay constant.
I mean, no, I mean,
But it's not the same. I mean,
no, so the length of the wave, no. So the velocity doubles because the length of the wave doubles, and t stays constant because the path doubles. The path the wave has to travel doubled. So you're looking at two lengths. You're looking at the length of the wave, and you're looking at the length of the path, right? So that doubles, and the velocity of the wave doubles, so the t stays constant.
we're saying the same thing.
Yeah.
So if the new pulse has the same frequency, what is the wavelength? Then it's then I say 2V over F then, correct?
If the new wave has the same frequency, the new pulse has the same frequency.
If the new wave pulse has the same frequency, what is the new wavelength?
Yeah, since you know that one thing always.
Find the wavelength. Define the first time.